So I want to talk about metabolism a little bit as we begin our new unit on cellular respiration. And before I can get into metabolism itself, I need to make sure that we all have a common understanding of energy and energy transformations. So the first thing that you need to understand is what is meant by the term kinetic energy. So kinetic energy is the type of energy that we talk about when we're talking about objects that are moving. Right, so it's very easy, I think, to picture mechanical kinetic energy, right? So if let's say a wheel is moving or a lever or something like that, we can see the object moving. We talk about microscopic or submicroscopic items. It gets a little harder, but the idea is still the same. So for instance, we can talk about thermal energy as being kinetic energy because the particles of that substance are actually moving and they'll move faster as the temperature increases. We can also talk about electrical energy as being kinetic energy because we're talking about moving charged particles. So both of those are examples of energy that is held by moving objects. Now, but there is also another form of energy that we refer to as potential energy, and that is essentially stored energy or energy that is waiting to be used, right? We can think of it as, that energy has the potential to do work, but it's just not being used at that time, right? So imagine that here I am on the top of a building and I've got a ball in my hand. Well, this ball has the potential to fall due to gravity. But at the time when I'm holding it, it's not doing anything. It just has the potential to fall. As soon as I release that ball, though, however, it no longer has potential energy. Well, it's losing potential energy, I should say. And that potential energy is being transformed into kinetic energy as it's moving. So in the same way, we can talk about there being potential energy in the bonds between between atoms. There is energy stored in that bond, and we can harness that energy by breaking bonds. And so broadly speaking, this brings me to the topic of thermodynamics, and we're going to have to investigate a couple of the laws of thermodynamics to make sure that we're on track for talking about metabolism. So what is thermodynamics? It's basically when we take a look at those energy conversions that are happening in matter from one form to another, so say for instance kinetic to potential, or kinetic to kinetic, and so on and so forth. What we're really talking about is just energy changes within a system. So the first law of thermodynamics you're likely familiar with. It states that energy cannot be created or destroyed, just transformed. And I think we know that anytime we take, let's say, electrical energy, and we're using that to power a light bulb, then we're changing that energy into from electrical into light energy and possibly some heat energy, some thermal energy. But the amount of energy in the universe is finite. We can't create any more than exists already, but we can transform it into different forms. So take, for instance, glucose. The glucose molecule has tons and tons of bonds. And by breaking glucose down, we're able to harness the energy that's held in its bonds and store it in a different form, in the form of ATP. So what do we do with that energy in the form of ATP? It's still chemical potential energy. Well, we use it to fuel all sorts of bodily processes. And for example, we can take that ATP and utilize it to push calcium ions in and out of muscle cells in order to cause our muscles to move, and that's mechanical energy. So in any chemical reaction, we're going to see bonds breaking and then bonds forming, right? And so when we're talking about the overall energy absorbed or released during a chemical reaction, it's all about the relative amount of energy that is used to break the bonds versus those required to maybe rebuild some bonds. And every reaction is different. And so that allows us to categorize whether a reaction is going to be considered exothermic or endothermic, right? All based on whether the amount of energy used to break bonds is less than, equal to, or greater than the amount of energy used to rebuild those bonds. So I want to briefly review the differences between exothermic and endothermic reactions in the context of biology. For some reason in biology, biologists like to use this word exergonic instead of exothermic, and instead of endothermic, endergonic. So just know that for the context of this course, both of those terms will be acceptable to me, but you may see either. So all molecules thrive if they're in their lowest energy state, and so that makes them stable. So when we're talking about an exothermic reaction, we have these reactants that have a certain amount of energy. This is on my y-axis I have chemical potential energy. So my reactants are going to have more energy, and then they're going to be transformed into products, and through that process their final energy is going to be lower than what it started with, right? They're just kind of taking a big exhale and releasing some energy. So in an exothermic reaction, it's not that there was no energy absorbed, it's just that the amount of energy released was greater than the amount that was absorbed. And of course, an endothermic or endergonic reaction, the product is going to be less stable because we actually have to add in energy into that system, into that molecule, to hold it together. And so it's not going to be in its lowest possible state. And you can see it here on the chemical potential energy graph that the reactant started at a lower energy. We're going to add energy into the system, and my products are going to have a higher amount of energy. So that's a far less stable molecule. In both of these cases, though, we do see that energy is going to be transformed. Either it's going to be transformed from chemical potential energy of one molecule to the chemical potential energy of another molecule or a series of molecules, but either way we're seeing that there is a transfer of that energy. So that brings us to the second law of thermodynamics, which is that every energy transfer or transformation is going to increase the entropy of the universe. So, well, what is entropy? Entropy basically describes the amount of disorder in something. So something with high entropy or increasing entropy is becoming more disordered, right? If you're decreasing the entropy, that means that this reaction that we're seeing here is going in reverse and things are becoming more ordered. Naturally, things in the universe tend to go from left to right here, becoming more disordered. So in every energy transfer, we're going to increase the disorganization or the disorder of the universe. So how does this apply when we're talking about energy? Well, it's important for you to know that heat is the most disordered or disorganized form of energy. And in fact, all energy can be quantitatively converted into heat. And we see that with light bulbs, incandescent light bulbs. We don't mean to create that heat energy, but because the transfer from electrical energy to light energy is so inefficient, there's a lot of heat released. Even a simple example like in our body when we digest food, the production of ATP from glucose is not 100% efficient, right? And so as a result of that, some of the ATP is transformed into heat, and or some of the energy from glucose is transformed directly into heat, and that heats our body, which is a good thing for us, but it makes the conversion of ATP from glucose not 100% efficient. So why do we care about any of this? Well, it's important for us to understand that exothermics, which are going to release energy, are going to power up the other reactions, the endergonic or endothermic reactions that require energy, right? So, the exothermic reactions are going to release the energy, and we're going to have that in the form of ATP. That ATP is then going to be used to power the reactions that need energy, right? And that's going to give us our ADP back, and then so the cycle continues on and on and on. That phenomenon is known as energy coupling. And so without those exothermic reactions, we wouldn't be able to power the endothermic ones. All right, so now I think we're ready to talk about metabolism. So, well, what is metabolism? We think about some people having fast metabolism or a high metabolism versus a low metabolism. What metabolism really means when we get down to the nitty-gritty of it is that it really just describes all of the anabolic reactions happening in our body. In other words, those reactions that are building things to make bigger things, and also the catabolic reactions that are going on in our body, so all the breakup reactions. So anabolic reactions, building things up, or decreasing the entropy. In other words, we're making things more organized, and that's going to require some energy. But those anabolic reactions are going to need to get powered by something. And in fact, it's the energy released from catabolic reactions that are going to provide the energy required to power up those anabolic reactions. Let's look at a diagram next so that I can kind of make this a little bit more visual for you. So metabolism, again, is just all of the anabolic reactions and the catabolic reactions happening in living things all the time put together. That's what metabolism is. And so, again, the anabolic reactions, we're going to put in some energy to take these molecules that are all kind of separate and smaller and to build them into something bigger. And in doing so, we are making something that is more ordered. In other words, we're decreasing the entropy of the universe. And nature tends not to want to go in that direction, which is why we need to input some energy in the first place. Catabolic reactions, we're going to take something big and break it down. Breaking those bonds is going to release energy, and that energy is going to get used over here to power up the anabolic reactions. So really, anabolic and catabolic reactions together are a great example of an energy coupling situation. So now we're going to sum things up, and I want to tell you where we're going with this, because the next step is, of course, to start breaking down the very large, very complex process of cellular respiration, beginning with glycolysis. So it's important for you to know that each step in a long metabolic process is going to involve many enzymes, and that's going to reduce the amount of energy required for the reaction. They are going to be reversible, and we're going to be looking at the reversibility of that in the next chapter on photosynthesis. And you're going to see that the reactions, glycolysis, for example, is basically a series of reactions, one after the other, where the product of one reaction is a reactant in the next. So, for example, molecule A becomes molecule B. So B was the product coming from molecule A, but then becomes the reactant used to make molecule C. And so here we have a series of chain reactions, different enzymes catalyzing each process. And so that metabolic process is going to involve sometimes energy being put in at a certain point and sometimes energy being released at a different point. So the final product is going to be excreted or precipitated out. So a good example of that would be in photosynthesis, we end up with some glucose, which is going to end up as starch. So that's our final product of that metabolic process. For cellular respiration, we're going to end up with some carbon dioxide and some water, and we are going to have to get rid of that in our system through the process of excretion. So be ready tomorrow for some questions. If you had any as you were watching this video, we'll discuss it briefly and then take the next step in our process of learning about cellular respiration.